Hello, and welcome to Sleep Night Space. Tonight, we're going to drift deep into the unknown, into the quiet questions that science has not yet solved. For all the discoveries we have made, the universe is still filled with puzzles, paradoxes, and deep mysteries that no one can fully explain. Some are cosmic, stretching across distant galaxies and black holes. Others live right here on Earth, in the deep oceans, the atmosphere, and even within the cells of our own bodies. These unanswered questions remind us that science is not a book of final truths, but an endless story still being written. Each mystery is a doorway to wonder, reminding us that we are explorers in a universe far bigger than we can yet comprehend. If you enjoy drifting off to these scientific wonders, you are welcome to like and subscribe, or simply share your thoughts in the comments. It helps others find their way here, too. But for now, get comfortable. Let your body rest. Let your thoughts wander. And let's begin. We still don't know why the universe exists at all. It seems like the most basic question imaginable. Why is there something instead of nothing? And yet, science has no answer. Physics can describe how the universe behaves once it exists. Cosmology can trace events back to the Big Bang. But why there is a universe at all, why there are laws that allow it to exist, remains unsolved. Quantum physics suggests that what we call nothing is not truly empty. Even the cold vacuum of space teems with quiet activity, fleeting particles that flicker into being before vanishing again. Some physicists suggest that the universe itself may have arisen in the same way. That absolute nothingness is unstable, and something must always emerge from the void. Others argue that perhaps our universe is only one of countless others in a vast multiverse, each popping into being with its own laws. But if that is true, we are only pushed back to a deeper question. Why should the multiverse itself exist? Philosophers sometimes propose that existence is simply the natural state, that non-existence is impossible. Perhaps reality in some form must always be, but these are ideas we cannot test. No telescope, no particle collider can measure why there is being instead of nothing. Every other question in science rests upon this one. Every star in the sky, every atom in your body, every law of nature, all exist on a foundation we cannot explain. The fact that reality is here at all remains the deepest mystery we face. The spark that set the cosmos in motion remains a mystery. We can trace the universe's story back nearly 14 billion years to an age when it was a hot, dense fireball. We call this beginning the Big Bang, but what actually caused it? That remains unknown. Cosmologists have pieced together a detailed history from the moment the universe was only fractions of a second old. In that first instant, a rapid expansion called inflation may have blown space itself wide open. But what triggered inflation? Why did it start and why did it end? These questions remain unanswered. Some theories imagine the Big Bang as a quantum fluctuation, a tremor in the fabric of reality that gave rise to space and time. Others suggest that the Big Bang was not the first event, but only one moment in a cycle of births and deaths, with universes expanding, collapsing, and beginning again. What complicates the question further is time itself. If the universe includes the birth of time, then asking what came before may not even make sense. Our instruments, the Hubble Space Telescope, the Planck satellite, and the new James Webb give us snapshots of the infant universe, but none can peer into the first instant itself. We know the universe began. We can measure its age, chart its growth, and study its afterglow. But the spark that set the cosmos in motion, the true first cause, is a mystery still hidden in the dark. Time always flows forward, but no one can explain why. Every moment, the present slips into the past. We remember yesterday, but not tomorrow. A broken glass never leaps back together. Heat moves from hot coffee into the air, but never the reverse. Time, in our experience, only flows one way. This is called the arrow of time. What makes it strange is that the fundamental laws of physics don't require this. At the smallest scales, particles can move forward or backward in time with equal consistency. The equations are symmetrical. Nothing in them demands that time should only advance. And yet, our entire world depends on this one-way street. Scientists often connect the arrow of time to entropy, the tendency for disorder to increase. The universe began in an exceptionally ordered state and has been running down ever since. But why did it begin that way? Why should the cosmos have started in such a low entropy? Condition that time could even have a direction. Some physicists think the arrow of time might emerge from the way information spreads. Others suggest it is tied to the expansion of the universe itself. But none of these explanations are complete. Time's direction is something we live inside of every second of our lives. And yet, why it flows forward and only forward remains one of the most haunting mysteries of science. Most of the universe is made of something we cannot see. When astronomers measure the way galaxies spin, they find something strange. Stars near the edges move far too quickly, as if held by an invisible force. By all logic, those stars should drift away into space. Instead, they remain bound. The conclusion is inescapable. Most of the mass in the universe is not visible to us. We call it dark matter. Dark matter neither glows nor absorbs light. Telescopes cannot see it directly. Yet, we know it must be there because its gravity shapes everything around it. It holds galaxies together, bends the paths of starlight from distant clusters, and leaves faint ripples in the pattern of the cosmic web. So what is it? Scientists have searched for decades. Some think it is made of undiscovered particles, perhaps WIMPs, weakly interacting massive particles. Others suggest axions, ghostly particles that barely interact with ordinary matter. There are even theories that dark matter could be ancient black holes, formed in the earliest moments after the Big Bang. Despite enormous effort, we still don't know. Experiments buried deep underground wait patiently for a passing dark matter particle to collide with a single atom. So far, none have. For now, this hidden mass, 5 times more abundant than ordinary matter, remains one of the universe's greatest unsolved mysteries. An invisible force is stretching space apart, faster and faster. In the 1990s, astronomers studying distant supernovae expected to see the universe's expansion slowing down. After all, gravity should be pulling galaxies back together. Instead, they discovered the opposite. The universe is not just expanding, it is accelerating. This means some unknown energy is embedded in space itself, pushing galaxies away from each other at ever-increasing speeds. We call it dark energy. though the name is only a placeholder for our ignorance. Dark energy makes up nearly 70% of the entire cosmos. Yet, we don't know what it is. One idea is that it is a property of the vacuum, a kind of constant energy present in empty space. Another possibility is that it points to new physics, perhaps a dynamic field that changes over time. Some theories even suggest it could be a sign that our understanding of gravity itself is incomplete. What makes the mystery even more unsettling is its consequence. The universe's fate depends on this invisible force. If dark energy remains constant, galaxies will drift farther apart until only empty space is left. If it grows stronger, it could eventually tear apart galaxies, stars, and even atoms. We can measure its effects, but we cannot see its true nature. Dark energy is the unseen hand shaping the ultimate future of the universe. The laws of physics seem tuned for life in ways we don't understand. The universe appears balanced on a knife's edge. If gravity was slightly stronger, stars would collapse too quickly. If it were weaker, galaxies might never form. If the electromagnetic force were different by a fraction, atoms would not bind together. Even the tiniest changes in the constants of physics could erase the possibility of life altogether. This puzzle is known as the fine-tuning problem. Why should the laws of nature have exactly the values they do? There is no obvious reason for gravity, electromagnetism, or nuclear forces to take the strengths they have. And yet, if they were different by even a little, our universe would be lifeless. Some argue this is a coincidence. Others suggest that countless universes exist, each with different laws, and we simply live in the rare one where life is possible, a cosmic lottery win. Another idea is that there may be a deeper principle still undiscovered that forces the laws to take these exact values. For now, we cannot say, but when we look around at stars, planets, and the fact that we can even ask this question, we are reminded that the universe feels improbably, uncannily suited for life. And why that is so remains one of science's greatest mysteries. No one knows if the universe goes on forever or ends somewhere. The observable universe is vast, about 90 billion light years across, but we cannot see beyond it. Light has only had so much time to travel since the Big Bang, and so there's a horizon we cannot look past. But what lies beyond that edge? One possibility is that the universe is infinite, stretching endlessly in all directions with no boundary at all. If so, then space may contain an unending number of galaxies, stars, and perhaps even other Earth-like worlds. Another possibility is that the universe is finite, but unbounded like the surface of a sphere. In such a universe, if you could travel far enough in one direction, you might eventually return to your starting point. Scientists search for answers in the cosmic microwave background, the faint afterglow of the Big Bang. Its patterns might reveal the universe's shape. So far, the evidence suggests that the universe is very nearly flat. But this does not settle the question of whether it is infinite. For now, we don't know if the cosmos stretches without end, or if it loops back on itself. The true size and shape of the universe remain hidden, just beyond our reach. Beyond the horizon of what we can see, there may be endless unknowns. When we look into space, we are also looking into the past. The most distant galaxies we can see are sending us light that has traveled for over 13 billion years. But beyond that lies a region forever hidden, the unobservable universe. This cosmic horizon is not like a physical wall. It is a limit set by the age of the universe and the speed of light. Beyond it, reality continues. But we can never know exactly what is there. Perhaps it is much the same: galaxies, stars, and planets stretching far beyond our sight. Or perhaps it is radically different, with regions governed by different conditions or even different physical laws. Some theories of inflation, the rapid expansion thought to have occurred right after the Big Bang, suggest that our observable patch is just one bubble in a much larger reality. If true, the vast majority of the universe lies forever beyond what we can measure. We are bound within a cosmic island. The sky we see is only the smallest fraction of what may exist. The rest of the universe is out there, silent, unreachable, and a permanent unknown. Some scientists believe there are other universes, but we cannot prove it. The idea of the multiverse is one of the boldest in modern science. It suggests that our universe may not be unique, but merely one of countless others. Each universe could have different laws of physics, different histories, and even different numbers of dimensions. The concept arises naturally in some theories. Inflation may create bubble universes, each budding off with its own unique conditions. String theory predicts a vast landscape of possible realities. In such scenarios, our universe is simply one outcome among many. This could even explain the mystery of fine-tuning. We live in a universe suited for life, simply because only in such universes can observers exist to see it. But there's a problem. If other universes exist beyond our cosmic horizon, we may never be able to observe them. No light or signal could ever cross that boundary. This makes the multiverse both fascinating and controversial. It stretches the definition of science itself, because an idea we cannot test may never be more than speculation. Still, the possibility that reality is larger than our universe, perhaps infinitely larger, is one of the most intriguing mysteries in physics. Space and time may be woven from deeper rules we haven't discovered yet. Einstein's general relativity shows us that space and time are not fixed backdrops, but flexible and dynamic. They bend, curve, and stretch, shaping the paths of planets and the flow of light. But what, at the deepest level, is this fabric made of? At the smallest scales, relativity and quantum mechanics clash. Space and time seem smooth in relativity, but quantum theory suggests that everything should be grainy, fluctuating, and uncertain. Reconciling these two views is one of the greatest challenges in science. Some ideas suggest that space and time are not fundamental at all. Instead, they may emerge from something deeper, perhaps a network of quantum information or entanglement patterns that give rise to geometry itself. In this picture, what we call space-time is like a surface, and underneath lies a more basic reality we cannot yet see. Others wonder if time itself is even real, or if it is an illusion created by deeper processes. If so, our most basic intuition about reality would be wrong. Space and time feel like the stage on which the universe unfolds. Yet the stage itself may not be what it seems. What they truly are remains one of the most profound, unanswered questions in science. A single particle can be in two places at once, and we don't know how. Quantum mechanics tells us that particles don't have definite positions until we measure them. Instead, they exist in a superposition, a kind of probability cloud where many outcomes are possible at once. An electron can be here and there, passing through both slits of an experiment simultaneously, interfering with itself like a wave. Only when we look does the particle choose a single place. This is not just theory. Experiments have shown superposition at work, not only with electrons, but with molecules thousands of times larger. Physicists can even create delicate states where objects exist in overlapping possibilities. And yet, no one truly understands what it means. Does the particle physically exist in two places? Or is superposition just a reflection of our incomplete knowledge? Some interpretations suggest multiple realities split. One where the particle lands here, and another where it lands there. Others suggest reality itself is fuzzy until it is measured. Whatever the case, the ability of a single particle to seemingly be in two places at once remains one of the strangest, most unsettling mysteries of modern science. Entangled particles echo each other across light years, defying explanation. When two particles become entangled, their properties link in a way that defies distance. Measure one, and you instantly know the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance, because it seemed to violate the cosmic speed limit. Nothing should move faster than light. Yet experiments confirm entanglement is real. Photons, electrons, even small groups of atoms have been entangled and separated by kilometers. No signal appears to pass between them, but the correlations remain perfect. It is as though nature itself keeps a hidden ledger, ensuring that the outcomes stay in sync. What does this mean? Some physicists suggest reality is non-local, that the universe is woven together more deeply than space and time allow us to imagine. Others think entanglement may point to hidden variables we haven't yet discovered. Still, others propose that information itself may be the foundation of reality. We use entanglement in quantum computing and secure communication, yet we cannot say why it works. The universe whispers across distance, and we still don't know how. No one knows why observing something seems to change what it is. One of the strangest discoveries in physics is that the act of measurement affects the system being measured. In the famous double-slit experiment, particles behave like waves when no one is looking, creating interference patterns on the screen. But if we measure which slit a particle goes through, the wave-like behavior vanishes. The outcome changes simply because we observed it. Why should this be? One explanation is that the wave function, the mathematical description of all possible states, collapses into a definite outcome when observed. But what counts as an observer? Is it a measuring device? A human consciousness? Or is collapse just an illusion, hiding deeper laws we don't yet see? Some interpretations say every possibility happens, branching into multiple universes. Others suggest that particles only appear definite when information about them becomes irreversible. None of these ideas have been proven. What we do know is that the line between observer and observed is not as simple as we once believed. The universe seems to care whether it is being watched, and no one knows why. Gravity is far weaker than every other force, and we don't know why. Gravity rules the cosmos. It holds planets in orbit, shapes galaxies, and governs the motion of stars. And yet, compared to the other forces of nature, it is unbelievably weak. A small magnet on your refrigerator can easily overcome the pull of the entire Earth. Why is this? The electromagnetic force, the strong nuclear force, and the weak nuclear force all operate on tiny scales with enormous power. Gravity, by comparison, is feeble. Physicists have tried to explain this hierarchy problem for decades. One possibility is that gravity spreads into hidden dimensions we cannot see, diluting its strength. Another is that the true scale of gravity is strong, but it is masked by unknown physics at small distances. Despite centuries of study, we still don't understand why gravity is so much weaker than the other forces. This imbalance is not just a curiosity. It is fundamental to the structure of the universe. Without it, stars and galaxies could not exist. The weakness of gravity is the quiet mystery that makes the cosmos possible. Einstein's general relativity and the quantum world both work, yet they refuse to fit together. General relativity describes the large-scale universe with unmatched precision. Quantum mechanics explains the microscopic world with astonishing accuracy. Each theory has been tested to extremes, and both pass every experiment we can throw at them. But they do not agree with each other. When we try to describe situations where both matter and gravity are quantum, like inside black holes or in the first moments of the universe, the equations break down. Infinity piles upon infinity. The two frameworks are mathematically incompatible. Physicists have searched for decades for a theory of everything that unites them. Candidates like string theory and loop quantum gravity offer tantalizing possibilities, but no experiment has confirmed them. Without a unifying theory, we cannot truly understand the birth of the cosmos or the nature of space-time at the smallest scales. The fact that our two most successful theories describe different realities is one of the greatest paradoxes in science. Both work perfectly, and yet together they fail. The true heart of a black hole remains unknowable. Black holes are regions where gravity is so strong that nothing, not even light, can escape. As matter falls inward, it is crushed toward the center. According to Einstein's equations, everything collapses into a single point of infinite density, a singularity. But infinity is usually a sign that our math has failed. What truly lies at the heart of a black hole? Some think the singularity is real, a place where the known laws of physics break down. Others believe a deeper theory, perhaps quantum gravity, will replace the singularity with something else, a loop of space-time, a finite core, or an entirely new kind of object we cannot see inside. The event horizon hides the interior completely from view. For now, the heart of a black hole is sealed away, beyond observation and beyond certainty. It remains one of the most inaccessible mysteries in all of science. We still don't understand what singularities really are. A singularity is a place where our equations predict infinities, density without limit, curvature without bound, time and space collapsing into something beyond definition. Black holes contain them. The Big Bang may have begun with one, but what are they really? Are singularities actual features of nature? Or are they signs that our theories are incomplete? Many physicists believe they point to the limits of Einstein's relativity. Somewhere beyond, a new theory, one that merges relativity with quantum mechanics, must take over. In that theory, the infinities might dissolve into something finite and describable. Until then, singularities remain puzzles at the edge of physics. They are places where our understanding stops and our models break. What lies beyond them is hidden, waiting for a deeper theory of reality. Whether information vanishes inside a black hole is an open question. When matter falls into a black hole, it seems to disappear forever. But in physics, information, the details about the state of a system, is supposed to be preserved. So what happens to the information locked inside? Stephen Hawking showed that black holes can slowly evaporate through radiation. But if they vanish completely, where does the information go? If it is destroyed, the laws of quantum mechanics would be violated. If it escapes, then somehow the information must leak out through the Hawking radiation, a process no one fully understands. This puzzle, known as the black hole information paradox, has challenged physicists for decades. Some think the information is stored on the event horizon itself. Others argue that black holes might connect to other regions of space-time, allowing the information to escape. Still others think our very understanding of quantum mechanics may need revision. The fate of information in a black hole is one of the most important open questions in physics. It touches not only on black holes, but on the deepest foundations of reality. Hawking radiation is predicted, but no one has ever seen it. In the 1970s, Stephen Hawking made a stunning prediction. Black holes are not truly black. Quantum effects near the event horizon should cause them to emit faint radiation, slowly losing mass over unimaginable timescales. Eventually, they could evaporate entirely. This radiation, now called Hawking radiation, is one of the most famous predictions in quantum physics. Yet, we have never observed it. Real black holes are surrounded by hot gas and violent environments that overwhelm the faint trickle of radiation. Detecting it directly may be impossible with current technology. Still, the idea has huge consequences. It ties together quantum theory, relativity, and thermodynamics. It suggests that black holes have a temperature, and that space-time itself is more dynamic than we realized. Laboratory experiments have tried to create analogs of Hawking radiation using sound waves and fluids. But these remain indirect hints. Whether Hawking radiation truly exists remains unproven. If it does, it will reshape our understanding of black holes. If it does not, something even stranger must be happening at the edge of space-time. Black holes may even be doorways to other worlds. We don't yet know. Black holes push physics to its limits. Inside them, space and time bend in ways we cannot fully describe. Some solutions to Einstein's equations suggest that black holes could connect to other regions of space-time, tunnels known as wormholes. In theory, entering a black hole might lead elsewhere. But this remains speculation. Wormholes, if they exist, may be unstable. The intense gravity of a black hole might destroy anything that tries to pass through. And yet, the mathematics leaves the possibility open. Some physicists suggest that the singularity at a black hole's center could mark a bridge to a new universe with its own space and time. Others think black holes might recycle information, seeding the birth of new cosmic regions. For now, we cannot test these ideas. No signal can escape a black hole's interior, and so its secrets remain hidden. Still, the idea that black holes may be more than cosmic graves, that they could be gateways to something beyond, is one of the most tantalizing mysteries of all. We still can't explain how the very first stars were born. When the universe was new, it was a dark, simple place. There were no galaxies, no planets, no metals or complex chemistry. Only clouds of hydrogen and helium drifted in the expanding cosmos. At some point, those clouds collapsed to form the first stars, ending the cosmic dark ages and lighting the universe for the first time. But exactly how this happened remains a mystery. These first stars, called population 3 stars, would have been enormous, hundreds of times the mass of our sun, burning hot and bright, but living only for a few million years before exploding as powerful supernovae. They seeded the cosmos with the first heavier elements, paving the way for later generations of stars, and eventually for life. The problem is, we have never seen one. No population 3 star has ever been observed. They lived and died so quickly, so long ago, that direct evidence is missing. Astronomers look for indirect clues in the chemical fingerprints of ancient stars, hoping to find hints of their violent births. The James Webb Space Telescope may finally glimpse their light. But for now, the exact process that sparked the first stars remains one of the great open questions in astronomy. Some galaxies formed supermassive black holes far too quickly. At the heart of nearly every galaxy lies a supermassive black hole, millions or billions of times more massive than our sun. We know how black holes can grow by swallowing gas, stars, and even other black holes. But in the early universe, we see black holes that grew far too large, far too fast. Some of these giants already existed less than a billion years after the Big Bang. According to our models, there simply wasn't enough time for them to grow so big through ordinary processes. This leaves us with a puzzle. Did they form from the collapse of enormous primordial clouds, skipping the small steps entirely? Did they grow from the deaths of massive first-generation stars that collapsed into black holes much larger than we expect? Or is there a mechanism we haven't discovered yet, allowing them to feed and expand at astonishing rates? These ancient black holes challenge our understanding of galaxy evolution. If we can solve their mystery, we may unlock the story of how galaxies themselves came to be. For now, they remain cosmic enigmas, giants that should not exist so soon after the universe began. No one knows why so many galaxies take on spiral shapes. When we imagine galaxies, we often picture elegant spirals, sweeping arms of stars curling outward like cosmic pinwheels. The Milky Way is one of them. But why should galaxies form such intricate spiral patterns? The answer is not clear. One idea is that spiral arms are density waves, like traffic jams on a highway. Stars move through them, bunching up as they pass, creating the illusion of permanent arms. Another theory suggests that spirals may be shaped by interactions, galaxies tugging on each other with gravity stirring stars into curving arms. Simulations can recreate spiral structures, but not with perfect consistency. Spirals are not rare. In fact, they are common. And yet, their exact origin and stability remain unsettled. Why some galaxies form beautiful spirals while others become elliptical blobs is still an open question in astrophysics. When we look at the night sky and see the Milky Way stretched across it, we're looking from inside one of these mysteries. Our home galaxy's graceful arms are both familiar and unexplained. Fast radio bursts flash across the cosmos, and their cause remains a mystery. In 2007, astronomers detected a powerful radio signal lasting only a few milliseconds. Since then, hundreds more have been found scattered across the sky. These signals are called fast radio bursts, or FRBs. Each one releases as much energy as the sun does in a year, but in the blink of an eye. What causes them? Some FRBs repeat, suggesting they come from ongoing processes like magnetars, highly magnetic neutron stars that can flare with incredible energy. Others appear only once, hinting at catastrophic events such as the collapse of a star or the merger of compact objects. But no explanation fits them all. FRBs travel across billions of light years, distorted and stretched by the matter between galaxies. They may even help us map the distribution of matter across the universe. But until we know their source, they remain cosmic puzzles. Every so often, the universe sends us a brief, powerful shout across the void. We can hear it, we can measure it, but we still don't know who or what is speaking. Pulsars shine with perfect regularity, but their precision still puzzles us. Pulsars are the collapsed remnants of massive stars, neutron stars that spin rapidly, sweeping beams of radiation across space like cosmic lighthouses. Discovered in 1967, they were so regular at first that scientists wondered if they might be signals from intelligent life. Today, we know they're natural, but their precision remains astonishing. Some pulsars keep time better than our best atomic clocks, rotating hundreds of times per second without missing a beat. How can an object so extreme, a star crushed into the size of a city, maintain such stability? The answer lies in their incredible density and strong magnetic fields. But the details are not fully understood. Pulsars can also glitch, suddenly changing their rotation speed in ways we cannot yet predict. These glitches may come from interactions deep within their superfluid cores, where physics is unlike anything on Earth. Pulsars are laboratories of extreme physics, but they still keep secrets. Their rhythms remain some of the most mysterious and precise signals in the universe. Magnetars erupt with strange bursts of energy we don't fully understand. A magnetar is a kind of neutron star with a magnetic field 1,000 times stronger than a normal neutron star, and 1,000,000,000,000 times stronger than Earth's. These magnetic fields twist and snap, releasing sudden, violent bursts of radiation. Magnetars can unleash more energy in a single second than the sun produces in 100,000 years. We detect them as intense X-ray and gamma-ray flares. But what exactly triggers these eruptions remains uncertain. Are the bursts caused by starquakes, shifts in the crust of a neutron star under magnetic stress? Or are they caused by sudden reconfigurations of a magnetic field itself? releasing energy like a snapping cosmic rubber band. Some fast radio bursts have even been linked to magnetars, suggesting they might explain at least some of those mysterious signals. But the full picture is still missing. Magnetars are rare, with only a few dozen known, but their power is staggering. They are reminders that the universe contains engines of energy we still struggle to comprehend. Cosmic rays strike Earth with incredible power, and we don't know where they come from. Every second, high-energy particles called cosmic rays rain down on Earth from space. Most are protons traveling near the speed of light. Many come from the sun or from supernovae, but some are so energetic, so powerful, that we have no idea where they originate. The most extreme cosmic rays carry the energy of a fast-pitched baseball packed into a single particle. No known process should be able to accelerate them to such speeds. They may come from supermassive black holes, from active galaxies, or from exotic processes we don't yet understand. These particles crash into Earth's atmosphere, creating showers of secondary particles that we can detect on the ground. Observatories like the Pierre Auger Observatory in Argentina track them, trying to trace their paths back to their origins. But magnetic fields in space bend their trajectories, erasing the clues. Cosmic rays are constant visitors, yet their most powerful examples remain unexplained. They remind us that somewhere in the universe, nature runs particle accelerators far beyond anything humans can build. Vast cosmic voids stretch across space, and their origins remain unclear. The universe is not evenly filled with matter. Instead, galaxies form a vast cosmic web, clusters and filaments separated by enormous voids. Some of these voids span hundreds of millions of light years, nearly empty of galaxies. Why are they there? Simulations suggest that gravity pulls matter into filaments, naturally leaving empty spaces behind. But the largest voids are bigger than expected, raising questions about how they formed. Do they hint at new physics? Perhaps in the way dark energy shapes structure? Or are they just statistical extremes? Rare but possible, voids affect how light travels across the universe. They may even offer clues about the nature of dark energy itself. But for now, their true origins remain uncertain. Looking into a cosmic void is like staring into nothingness on the largest possible scale. They're among the loneliest regions in existence. Vast expanses with no clear explanation. How the universe will end is still an unanswered question. The universe had a beginning, but will it also have an end? Scientists consider several possibilities, each dependent on the nature of dark energy and the balance of cosmic forces. In one scenario, the universe expands forever, cooling until stars burn out and galaxies fade, leaving only cold darkness. This is the heat death. In another, the expansion may eventually reverse, pulling everything back together in a big crunch. A third possibility is the Big Rip, where dark energy grows stronger over time, tearing apart galaxies, stars, planets, and eventually even atoms. Which will it be? We don't yet know. Observations suggest expansion will continue, but the details of dark energy remain too uncertain to decide. The universe may last for trillions of years, or it may meet a more dramatic fate. For now, the ultimate future of everything, of stars, galaxies, and life itself, remains one of the greatest unanswered questions of science. Something triggered cosmic inflation, but no one knows what. In the earliest fraction of a second after the Big Bang, the universe is thought to have expanded faster than the speed of light in a process called inflation. This theory explains why the cosmos appears so smooth and uniform, and why tiny fluctuations seeded the galaxies we see today. But what caused inflation? That remains a mystery. Some theories propose a field of energy, the inflaton, that briefly dominated the universe before fading away. Others suggest inflation is tied to the quantum structure of space-time itself. We see its fingerprints in the cosmic microwave background, where patterns match what inflation predicts. But the true cause, and whether inflation really happened as described, is still debated. Something made the universe grow unimaginably fast, creating the stage for everything that followed. But the spark that drove this inflation is still unknown. A hidden chapter in the story of creation. The origin of life on Earth is still unknown. Life on Earth began more than 3.5 billion years ago, but the details of its origin remain hidden. Fossil evidence shows that microorganisms were already thriving not long after the planet cooled. But how did non-living chemistry cross the threshold into life? One theory is that life began with simple molecules self-organizing into chains capable of storing information. Perhaps RNA came before DNA. Another is that life emerged from the energy-rich environment of hydrothermal vents on the ocean floor, where hot water, minerals, and chemistry combined. Still others propose that life's building blocks may have arrived from space, carried on comets or meteorites that bombarded the young Earth. Each idea has support, but none are proven. Scientists have managed to create amino acids and other basic molecules in laboratory conditions thought to mimic the early Earth. But producing a fully living system remains beyond reach. The origin of life may have been a unique event, or it may be a natural outcome whenever the right conditions exist. Until we uncover clearer evidence, the moment when chemistry first awakened into biology remains one of science's deepest mysteries. We don't know if life began in the ocean or on land. Our planet offered many possible cradles for the first life. The ocean, covering much of Earth, seems like the obvious candidate. Hydrothermal vents, where hot water and minerals pour from the seafloor, provide rich chemistry and constant energy. Many scientists believe life may have begun there, with molecules assembling inside natural mineral compartments. But there is another possibility. Some researchers argue that shallow pools on land, subject to cycles of drying and refilling, could have concentrated molecules and driven the reactions needed to form life's building blocks. Ultraviolet light from the sun, often destructive, could also have powered key steps in these reactions. Both environments seem plausible. Each offers strengths, and each faces challenges. The ocean dilutes molecules, making it harder for them to interact, while land-based pools may have been too unstable. Until stronger evidence emerges, we don't know whether life first stirred in the deep oceans or in the shallow waters of land. The answer remains hidden in the deep past, in rocks and fossils that have long since transformed. No one knows how the first living cells were formed. Life is defined not just by chemistry, but by organization. Modern cells are intricate structures with membranes that separate them from the outside world, and with molecular machines carrying out countless reactions. But how did the first cell arise from lifeless chemistry? One possibility is that fatty molecules, naturally present on the early Earth, formed bubbles that trapped useful chemistry inside. These primitive membranes could have allowed energy and molecules to flow while protecting fragile chains of RNA or proteins. Over time, the chemistry inside could have become more complex, eventually becoming self-sustaining. Experiments show that simple membranes can indeed form spontaneously in the right conditions. But how the leap from these primitive compartments to the complexity of a living cell occurred is still unknown. This transition from disorderly chemistry to the first organized cell remains one of the great mysteries of biology. Until we understand it, we cannot say how life truly began. DNA chose a very specific shape, but why it did remains a mystery. All life on Earth uses the same molecule to store information, DNA. Its double helix is elegant and universal, carrying the instructions for every organism. But why this molecule? And why this shape? Chemistry allows for many possible ways to store information. RNA, for instance, is simpler and may have come first. But somewhere in life's early history, DNA took over as the master code. Consciousness arises from the brain, but we don't know how. Every thought you have, every memory, every flicker of awareness seems to arise from the physical matter of the brain. Scientists can measure electrical signals moving across neurons. They can track activity when you focus on a picture or a sound. Yet, none of this explains why there is an inner experience at all. Why should firing neurons create the feeling of being alive? A brain scan can show activity in the visual cortex when you see a sunset, but it doesn't explain why that experience comes with the glow of red and gold inside your mind. Researchers have ideas that consciousness appears when information spreads across the brain, or when neurons form certain patterns. But none of these ideas truly explain the leap from matter to mind. Consciousness is the most ordinary thing, is what you are experiencing right now. And yet, when we try to explain it, it slips through our fingers. We know it arises from the brain, but the how remains the deepest mystery of all. Dreams fill our nights, but their purpose is still unknown. Every night, as you sleep, your mind conjures worlds. Some are vivid, filled with people and places you know. Others are strange and fragmented, dissolving as soon as you wake. These are dreams, and though we all experience them, no one truly knows why they happen. Some scientists think dreams are the brain's way of practicing. They may replay memories, strengthening useful connections. Others believe dreams help regulate emotion, allowing you to work through feelings in a safe, unreal space. Some say they're simply random firings of sleeping brain patched together into stories. We know the brain is active while we dream, especially during REM sleep, but the purpose behind it remains elusive. Dreams are familiar nightly journeys into strange lands, yet their true meaning is still hidden. Time feels slower or faster depending on us, and no one knows why. Think of a moment when time seemed to slow to a crawl, a sudden fright, an intense experience. Now think of the opposite. Hours that disappeared when you were fully absorbed in something you loved. Clock time is steady, but our sense of time is anything but. Why? No one knows for sure. Some believe the brain has an internal clock that emotions can speed up or slow down. Others suggest our brain judges time by the number of new memories it processes. A moment filled with new details feels longer. A routine, one feels shorter. What we do know is that time in the mind is elastic. It stretches, contracts, and sometimes even seems to stand still. The seconds are constant, but our experience of them is mysterious. We don't yet understand how memories are stored and recalled. Your entire life, your first day of school, your happiest moments. Memory is stored somewhere inside your brain. And yet, how those memories are kept and how they return when you need them is still a mystery. Scientists know that memories are not like files in a cabinet. They are patterns of activity spread across many neurons. The hippocampus helps weave these patterns, acting as a kind of index. But exactly how the brain encodes a memory and later pulls it back is not fully understood. Sometimes memories change when we recall them. Sometimes we even create false memories that feel completely real. Memory is the glue that makes us who we are, and yet the machinery behind it remains unknown. Our emotions run deep, but their origins remain mysterious. Emotions shape every part of life. Joy pushes us forward. Fear holds us back. But where do they come from? Scientists know that emotions involve the body as well as the brain. Your heart races, your stomach knots. But are emotions hardwired ancient survival tools? Or are they constructed by the brain, shaped by culture and memory? We know certain brain regions play a role, like the amygdala, but no single emotion center exists. Emotions are powerful guides, often steering our choices more than reason does. Yet the way they arise remains one of the most intimate mysteries of being human. Creativity appears in sudden sparks, but we don't know where it comes from. An artist stares at a blank canvas. A scientist, an unsolved problem. Hours may pass with nothing, and then suddenly an idea arrives. Clear, surprising, alive. Where did it come from? Creativity feels like a spark, but its origin is hidden. Some say it is the brain mixing old ideas in new ways. Others think it requires letting the subconscious work while the conscious mind rests. Many breakthroughs in history have come not at desks, but in dreams or quiet walks. Creativity is one of humanity's greatest gifts. Yet the place where ideas come from, that quiet leap from nothing to something, is a mystery we still cannot explain. Deja vu makes the present feel repeated, and no one knows why. You step into a room you've never been in before, and suddenly, everything feels strangely familiar. You feel like you know what will happen next. This is deja vu. Scientists suggest it may be a trick of memory. Misfiring in the brain, creating a false signal of familiarity. Others think it happens when one part of the brain processes an experience slightly before another. Almost everyone experiences it, yet no one can predict when or why. Deja vu reminds us that perception is fragile and that the brain sometimes plays tricks we don't yet understand. Placebos can heal, but the power behind them is still a mystery. Imagine taking a pill, being told it will ease your pain, and then actually feeling better, even though the pill contained nothing at all. This is the placebo effect, and it is real. Doctors have seen placebos reduce pain and even calm symptoms of disease. The effect is thought to come from expectation. The belief that something will help triggers real changes in the brain and body. Placebos can release natural painkillers and alter brain chemistry. But why some people respond strongly to placebos and others do not is still unknown. It shows us that belief itself can sometimes heal in ways we still don't fully understand. We don't even know why we need sleep at all. Every night, we surrender to sleep. We close our eyes, drift into dreams, and lose awareness for hours. But why? Sleep is dangerous in the wild. An animal that sleeps is vulnerable. Yet every species does it. That suggests sleep is essential. But essential for what? Some scientists believe sleep helps the brain store memories. Others think it clears away waste, cleaning the brain of harmful buildup. Sleep may restore energy or regulate emotions. And yet, no single explanation fits all the evidence. What we know for sure is that without sleep, minds and bodies break down. Why we spend a third of our lives doing it remains one of science's great mysteries. We still don't know why aging happens the way it does. Every living being on Earth ages, but science cannot fully explain why, or why it happens so differently across species. One explanation points to our DNA. The protective caps on our chromosomes, called telomeres, grow shorter. Another theory blames damage accumulating in cells over time. Others see aging as a side effect of evolution. Yet nature presents exceptions. Some turtles and fish show almost no signs of aging. Certain jellyfish appear able to revert to earlier stages of life. Naked mole rats live far longer than expected. Why do some creatures resist aging while humans succumb to it? The answers remain elusive. For now, aging is a riddle written into our very cells. The limits of human lifespan remain uncertain. The longest confirmed human life ended at 122 years. But was this the upper ceiling of human biology, or just an outlier? Some researchers argue that humans have a hard limit. Others insist there is no strict maximum. What's puzzling is that although average life expectancy has climbed, the maximum lifespan has barely budged. The upper boundary of human life remains hidden, waiting for someone to discover if it can be pushed further. Some animals can regenerate entire limbs, and we can't explain how. If a salamander loses a leg, it grows a new one. If a starfish loses an arm, it rebuilds it. In nature, regeneration is surprisingly common, but humans cannot do it. Why them and not us? Scientists find that when salamanders are injured, their cells seem to reset, rolling back into a flexible state. Humans share many of the same genes, yet for reasons we don't understand, our bodies do not use them in the same way. If we could unlock this ability, medicine would be transformed. For now, regeneration belongs to the salamander and the starfish. A miracle we can only watch with awe. Certain creatures live far longer than expected, and we don't know why. Most animals follow a simple pattern. Small bodies live short lives. Large ones live longer. But scattered across nature are creatures that defy these rules. The Greenland shark glides beneath Arctic ice for centuries, living more than 400 years. Bowhead whales sing in frozen seas for over 2 centuries. Some clams have been discovered alive after 500 years. Why? Scientists have found clues: efficient DNA repair, slow metabolisms, but no single answer explains them all. These creatures remind us that aging is not a fixed law, but a puzzle with many solutions. Some animals survive being frozen solid, yet their secrets remain hidden. Imagine being frozen into ice. Your heart silent, your body rigid. For the wood frog of North America, this is not death. It is winter. When spring returns, the frog thaws and hops away unharmed. Tardigrades, tiny water bears, can endure extremes far beyond freezing. How do they do it? Some use natural antifreeze molecules to protect their cells. But the exact details of how delicate organs survive months without activity remain unclear. The secret belongs only to these hardy survivors. Whales live for centuries without much cancer, and no one knows how. This is known as Peto's paradox. Large animals with more cells should have higher cancer rates, but whales and elephants don't. Somehow, they resist. In elephants, researchers found extra copies of tumor suppressor genes. In whales, the explanation is murkier. Perhaps their DNA repair is unusually strong. If we could unlock this mystery, it might revolutionize medicine. But for now, the secret drifts beneath the waves. Birds can sense Earth's magnetic field, but the mechanism is still unclear. Every year, birds migrate across continents with uncanny accuracy. Part of their secret seems to be Earth's magnetic field. But how? They sense it remains uncertain. Some evidence points to tiny crystals of magnetite in their bodies. Other research suggests proteins in their eyes may let them see magnetic fields. Whatever the method, it is a sense humans lack, an invisible layer of reality we cannot perceive. Monarch butterflies navigate continents with a map we cannot read. Every autumn, fragile monarchs fly thousands of miles to Mexico. What makes this migration astounding is that no single butterfly completes the round trip. The ones that return north are several generations removed. Yet somehow, they arrive at the same groves. How do they pass this knowledge between generations? It is a mystery hidden in their instincts. Migrating animals cross thousands of miles, but we don't know how they guide themselves. Salmon return to the stream where they hatched. Sea turtles return to the same beach. Scientists have found clues, stars, the sun, scents, but none fully account for the precision. Migration is one of life's oldest rhythms, a mysterious dance written into nature. Homing pigeons return home from anywhere, and the mystery persists. Release a pigeon hundreds of miles away, and it flies straight back. No map, no guide. Researchers have proposed the sun, magnetic fields, even smell, but none fully explain the uncanny accuracy. It is a secret compass we have yet to uncover. No one knows exactly how humans first developed language. Language makes us human, but how it began remains one of the greatest mysteries of our past. At some point, our ancestors made the leap from simple calls to structured language. Did it begin as hand signals or rhythmic chants? Language allows us to plan, dream, and imagine. Yet the first spark of language, the moment humans first spoke, is lost in time. Laughter is universal, but its roots remain a puzzle. Wherever you go, people laugh. Some scientists believe laughter began as a signal of safety. Others trace it back to primates at play. But laughter is more than survival. It bonds groups and releases stress. We laugh at jokes, but also at relief, or even sorrow. Laughter is the music of joy, yet its evolutionary roots are hidden. Music moves us deeply, but science can't explain why. A melody can make us cry. A rhythm can make our hearts race. Music has no obvious survival function, yet it shapes every culture. Some suggest music evolved to bind communities. Others think it is a byproduct of language. Music is an invisible thread that ties us together, a mystery of the human mind. Love is powerful and complex, but its full nature is still unknown. Love shapes human lives. Biology shows us chemistry, dopamine, oxytocin. Evolution suggests it keeps parents together. But these do not capture the full experience. Why does love arrive suddenly? Why do people risk everything for it? Love is both universal and unique. Its full nature remains one of the most profound mysteries of being alive. Humans cry tears of emotion, and no one knows why. Only humans shed tears for feelings. Sadness, joy, frustration. One idea is that tears are a social signal of vulnerability. Another is that they release stress chemicals. Tears make the invisible visible, carrying feelings to the outside world. But the reason we alone evolved this response remains unsolved. Myths appear across cultures in similar forms for reasons we don't understand. Flood myths, sky gods, tricksters, stories separated by oceans echo one another. Some suggest human minds are wired for story. Others believe ancient myths spread through migration. Whatever the reason, myths carry truths that bind communities. The recurrence of these stories remains a mystery. We often cooperate with strangers, and the origins of this instinct are unclear. Humans help strangers. We donate, we build, we sacrifice. Evolutionary theories suggest cooperation strengthens groups, but humans go beyond calculation. Something in us seems drawn toward cooperation, a moral instinct written into our minds. Civilizations rise and fall, but the deep forces behind them remain debated. The Maya, Rome, Mesopotamia, all rose, all fell. Why? Climate? War? Resource exhaustion? Or do civilizations carry natural cycles of growth and collapse? History reminds us that nothing lasts forever. The reasons why remain a mystery. Human curiosity drives us, but its source is still unknown. Why do we wonder? Why we look up at the stars? Curiosity drives us to explore galaxies and decode ancient languages. It seems built into us. But this restless hunger for knowledge, the spark behind the question why, is still one of life's mysteries. Storytelling is universal, but no one knows why we need it. Every culture tells stories. They entertain, teach, and inspire. But why are they universal? Stories create worlds that never existed and fill us with emotions. No other species does this. Storytelling is as ancient as language itself, a thread connecting us all. We don't know if true randomness actually exists. Flip a coin, roll dice, shuffle cards. Randomness seems obvious, yet physics makes the question stranger. At the quantum level, particles behave unpredictably. An electron may appear here or there. A radioactive atom may decay now or later with no cause we can see. Is this true randomness? or just complexity beyond our understanding. Einstein famously resisted the idea, saying, God does not play dice with the universe. He believed hidden laws must govern quantum events. But decades of experiments suggest otherwise. Quantum mechanics really may be irreducibly random. Still, some scientists believe deeper rules are waiting to be discovered. Others think randomness is woven into the very fabric of reality. If true randomness exists, then uncertainty is not just ignorance. It is part of what reality is. Whether the universe is fundamentally ordered or truly random remains an unanswered question at the heart of physics. Time itself is still one of science's greatest mysteries. We live in time. We feel it flow, second by second, carrying us from past to future. Yet science cannot fully explain what time is. Einstein showed that time is not absolute. It bends and stretches depending on speed and gravity. A clock on a mountain ticks faster than one at sea level. A clock in orbit ticks differently than one on Earth. Time is woven with space into a single fabric. But why do we experience it as a one-way arrow? Why does the past feel fixed while the future remains open? Some physicists think the arrow of time is tied to entropy, the tendency of disorder to increase. But this only pushes the question back. Why was the universe born in such an ordered state? Others suggest time itself might be an illusion, a trick of human perception. Time governs every heartbeat, every thought, every life. Yet its true nature remains one of the most profound mysteries we face. Matter exists, but antimatter nearly vanished. We don't know why. When the universe began, the Big Bang should have created equal amounts of matter and antimatter. But when matter and antimatter meet, they annihilate into pure energy. If they had been perfectly balanced, everything should have disappeared in a flash of light, leaving no stars, no planets, no people. And yet, here we are. Somehow, matter won. Why did matter gain the upper hand? Experiments show that matter and antimatter behave almost identically, but with tiny asymmetries. These slight differences may have tilted the balance in the early universe, but they do not seem large enough to explain why anything exists at all. Somewhere in the physics of the early cosmos lies the reason why there is something instead of nothing. Until we find it, the victory of matter over antimatter remains an unsolved riddle. Particles have mass, but we still don't know what gives it to them. Everything around us has mass, from stars to sand to our own bodies. But what gives particles mass at all? For decades, this was one of physics' biggest mysteries. The discovery of the Higgs boson in 2012 confirmed that an invisible field pervades the universe. As particles move through it, they acquire mass, like swimmers pushing against water. Without this field, matter as we know it could not exist. But the Higgs mechanism answers only part of the question. Why does the Higgs field itself exist? Why does it have the strength it does? And why do different particles interact with it so differently? The Higgs discovery opened the door, but behind it lies a deeper mystery still. Mass feels solid and obvious, but its origins remain partly hidden in the invisible fields of the cosmos. Reality may be continuous, or it may be pixelated. No one knows. To our eyes, reality feels smooth. Space seems infinitely divisible, like a line you can cut forever. But at the smallest scales, physics may be different. Some theories suggest the universe is pixelated, made of tiny, indivisible units, like the pixels on a screen. If reality is pixelated, then space and time themselves are not smooth, but granular. The rules of physics would need rewriting, but so far, no experiment has confirmed this. Whether the universe is continuous or digital remains one of the strangest questions in science. The answer could reveal the true texture of reality itself. There may be a smallest possible length of space, but we haven't found it. Physics pushes us to ever smaller scales. Atoms, once thought indivisible, were split into protons and electrons. Protons themselves turn out to be made of quarks. Yet at some point, there may be a smallest length, a limit beyond which smaller has no meaning. This is thought to be the Planck length, unimaginably tiny, about 100 billion times smaller than a proton. At this scale, space may no longer be smooth, but foamy and uncertain, a quantum haze. But no experiment can reach it yet. If space has a smallest unit, then the universe is not infinitely divisible. Reality would have a bottom floor, the smallest brick of existence. Whether such a limit exists remains one of the deepest mysteries of physics. The laws of physics could have been different, but no one knows why they are what they are. The universe runs on laws. Gravity, electromagnetism, quantum mechanics. They are elegant, precise, and consistent. But they could have been otherwise. Why this set of laws and not another? Why a universe where stars can form, instead of one where matter collapses or drifts apart? Some scientists imagine countless universes, each with different laws. And ours is simply one where the conditions allow life. Others think deeper principles, still unknown, fix the laws in place. But for now, the origin of the laws themselves remains unexplained. We can describe the rules. We cannot yet explain why these rules, and not others, are written into reality. And perhaps the greatest mystery of all, whether we will ever truly understand any of this. Science has carried us far. We have mapped galaxies, split atoms, decoded DNA, and walked on the moon. Each answer reveals more questions. Each discovery opens new mysteries. Perhaps one day we will explain consciousness, the origin of life, the birth of the universe, the nature of time itself. Or perhaps there will always be questions just beyond our reach. Mysteries that cannot be solved because they are woven into the fabric of existence. The greatest mystery may not be the universe itself, but our place within it. Whether human minds can ever truly comprehend the totality of reality. As you drift to sleep, you might hold that thought gently. That curiosity itself is part of the mystery. To wonder is to be human, and to seek is to be alive. The questions may never end, but neither will our search. You just traveled through 100 of science's greatest mysteries. Questions that stretch from the cells in our bodies to the edges of the universe itself. Each one is a reminder that for all we've discovered, the world remains far deeper, stranger, and more beautiful than we can fully grasp. Think of what we've touched tonight, the hidden spark of consciousness, the riddles of aging and memory, the secrets carried by oceans beneath icy moons, the timeless puzzles of stars, storms, and the fabric of reality itself. Some of these questions may be answered in your lifetime. Others may remain mysteries for generations, and still others may never be solved at all. But that is part of the wonder. To live in a universe that still holds so much unknown is to live in a universe filled with possibility. Every unanswered question is an open door. Every mystery an invitation. The fact that we don't yet know keeps science alive, keeps curiosity burning, and keeps us leaning forward into tomorrow. And as you lie here now, letting the weight of these mysteries drift across your mind, notice how gently they pull you toward rest, like the slow rhythm of waves on a shore. The questions themselves are soothing. They don't need answers tonight. They only need to be carried, like starlight across a dark sky. So let your breathing fall into rhythm. Let your body grow heavy and your thoughts soften. Imagine yourself floating through the mysteries we've explored, passing by them as if through constellations in the night. Questions above, questions below, a galaxy of wonder all around you. And you, at the quiet center, resting in the knowledge that mystery is not something to fear, but something to embrace. If you happen to still be awake, you can go ahead and watch the next video when you're ready. But for now, there's nothing left to do. No answers to chase. No puzzles to solve. Just the calm certainty that mystery itself is a kind of lullaby, one that will carry you into sleep. Good night, and may your dreams be filled with